Interceptor missiles cost millions. Attackers now spend far less. For every $1 spent on offense, defense spends $6 to keep up, yet it is still not enough. The real problem is not failed technology. It is relentless math that military budgets cannot defeat. Why is the missile shield so overwhelmed, and how much wider can the gap get before defense becomes unsustainable? A single interceptor missile can cost anywhere from a few $100,000 to tens of millions of dollars. The Iron Dome Tamir interceptor, designed for short-range rockets and drones, is priced between $40,000 and $60,000 per shot. For medium and high-altitude threats, the cost rises sharply. A Patriot Pack 3 MSE interceptor is typically $3 million to $5.5 million each. Terminal High-Altitude Area Defense, THAAD, sits even higher at $12 to $15 million per unit. Mid-course interceptors like the SM-3 Block 2A sometimes reach $28 to $36 million apiece. On the other side, the price tag for offensive weapons is a fraction of that. Unguided rockets and artillery rounds used in saturation attacks often cost a few $100s each. Loitering munitions and small attack drones can be built for less than $1,000 in some cases, with more advanced models, like the Shahed 136 drone, falling in the $20,000 to $50,000 range. Cruise missiles, though more sophisticated, generally cost between $500,000 and $1 million per unit, while short-range ballistic missiles from regional arsenals might reach into the low millions. These figures are not outliers. They are averages drawn from recent procurement records and open-source conflict data. The result is a gap that grows wider with every new system. For every $1 million spent on a defensive interceptor, attackers can field dozens, or sometimes hundreds, of offensive weapons. This imbalance is built into the economics of modern missile warfare, shaping every engagement before a single shot is fired. A defense economist once described the arithmetic of missile defense as a kind of cruel math. Suppose an attacker launches 50 cruise missiles, each costing around $500,000. The total bill for the offense is $25 million. Now the defender must respond with 50 interceptors, such as Patriot Pack 3 MSEs, at $3 million each. That is $150 million spent in a matter of minutes, 6 times the attacker's outlay. The calculation does not end with the money. If the defense claims a 90% interception rate, the expected survivors equal 50 times 10%, which is 5 missiles. In this scenario, even after spending 6 times as much, the defender still absorbs 5 successful hits. The numbers are not theoretical. The expected survivors formula, N times 1 minus P, appears in nearly every defense analysis. N is the number of incoming missiles. P is the probability of intercept. The result shows how many warheads slip past. This is not a rare outcome. If the defender's success rate drops to 85%, the number of surviving missiles climbs to 8. The cost gap remains, $150 million versus $25 million, but the risk grows. As The Economist put it, missile defense drains resources with every launch, while offense simply loses inventory. The arithmetic favors the attacker, and every salvo makes the imbalance more visible. A modern missile attack rarely comes as a single threat. Instead, attackers combine drones, cruise missiles, and decoys in tightly packed salvos designed to overwhelm every layer of defense. Each missile defense system, Patriot, Iron Dome, Aegis, relies on radars and fire control computers to track, classify, and intercept incoming objects. But these systems have hard limits. A typical high-end radar might track 100 to 200 objects at once. Fire control channels, which guide interceptors to targets, are even more constrained, often capped at about 20 engagements per minute per battery. When the number of incoming threats exceeds these limits, the system is forced to drop or ignore tracks, letting some threats slip through untouched. The 2019 strike on Saudi Arabia's Abqaiq oil facility exposed these limits. 25 drones and cruise missiles approached from multiple directions at low altitude, saturating the radar's field of view. Operators reported that their systems could not engage every target. Some objects vanished from the queue before a single interceptor could be launched. A fire control engineer described the result. Missile defense does not break at 0%, it breaks at 80%. Even with a claimed 80 or 90% success rate, once the number of threats crosses the system's capacity, the last wave arrives unopposed. Attackers exploit this non-linear failure. Mixed salvos are designed to compress arrival times, saturate sensor channels, and force defenders to make impossible choices about which threats to engage. The tipping point is not gradual. It happens suddenly, as queues fill, and the defense's ability to respond collapses. The gap between theory and reality widens with every new salvo. The consequences are measured not just in missed targets, but in the speed at which defenses are exhausted. Speed alone no longer defines the threat. Hypersonic glide vehicles, now fielded by Russia and under development in China and the United States, travel at velocities greater than Mach 5, over a mile per second. But it is their ability to maneuver unpredictably during flight that fundamentally changes the equation. Traditional missile defense systems rely on projecting a target's path from launch to impact, using radar data and physics models built for ballistic arcs. These models work when missiles follow predictable, parabolic trajectories. Hypersonic gliders break that assumption. They can shift laterally, climb, or dive at any point along their flight, rendering early predictions obsolete within seconds. Time to detect and decide has collapsed. Where a conventional intercontinental ballistic missile might give 10 to 30 minutes of warning, a hypersonic glide vehicle can cut that window down to single-digit minutes. Operators must make identification and engagement decisions in a fraction of the time they once had. The geometry of interception becomes exponentially harder as speed and maneuverability increase. A small error in prediction at Mach 5 or above results in a miss by miles, not meters. Every layer of defense, including radar, command, and interceptor systems, depends on the ability to forecast where a threat will be. Hypersonic maneuvering erases that predictability. The challenge is not just speed, but the loss of certainty. Missile defense, built on the premise of prediction, faces a class of weapons designed to erase that advantage entirely. Every missile defense engagement starts a race against the clock. The chain begins with radar detection. Seconds matter as sensors pick up a launch. Operators must classify the threat, decide if it is a drone, a cruise missile, or something else, and authorize a response. Each link in this chain is measured in minutes, sometimes less. In January 2022, air defenses in Abu Dhabi faced a mixed attack. Drones and a ballistic missile were detected almost simultaneously, forcing defenders to move from detection to interceptor launch in under 5 minutes. With hypersonic and low-altitude threats, that window shrinks even further. Automation speeds up the process, but it also increases the risk of mistakes, including misidentification or accidental escalation. The margin for error is now measured in heartbeats. Missile defense is running out of time before it runs out of missiles. Missile defense systems regularly pass scripted tests, but these exercises operate under conditions that rarely match the chaos of real combat. Each test is run with advance notice, a single incoming missile, and detailed telemetry shared between the launch and intercept teams. The target follows a known trajectory, often without decoys or electronic interference, and the engagement unfolds in a controlled environment. In contrast, actual attacks arrive with no warning from multiple directions and involve a mix of drones, cruise missiles, and ballistic threats. Sensors must sort through clutter and ambiguity, while operators face compressed timelines and incomplete information. The ground-based mid-course defense system, for example, has demonstrated success against isolated targets in rehearsed scenarios, but has never been tested against a mass salvo or a maneuvering warhead. Passing tests in the lab does not guarantee survival in the field. Missile defense is no longer a guarantee. It is a costly margin of delay against threats that multiply and adapt faster than budgets or blueprints. Today, deterrence depends less on interceptors and more on uncertainty. The shield still stands, but its limits are clearer than ever. What comes next is not a technical question.